So now we want to talk about problem of ideal inventory. So consider there is an ice cream shop and the demand is a random variable x. So ice cream shop has some demand and the demand is a random variable, but that demand has a probability density function which is small f of x. So the shop carries an inventory of t units. Now the cost is a function of the units it carries and the random variable. So if the demand x or the random variable x is less than the inventory you carry, so you are carrying t units, and the random variable is less than or equal to t, then the cost is a times t minus x. On the other hand, if the demand is greater than the units you carry, there is still cost associated with it, which is b times x minus t. So you can say that you still have to keep the shop open, and you have some refrigeration cost and maybe some hiring cost, even if you run out of stock, because t is the stock and x is the random demand. So although you have run out of the stock in the case x is greater than t, you still have costs associated. And similarly, when x is less than or equal to t, that is the demand is less than the units you carry, you still have the cost, which is a times t minus x. So this is the setup of the problem. So we want to find what is the optimal value of inventory you should carry. So we are right now carrying t units and we want to find what is the optimal value of t. So what is the expectation of this cost function? So expectation will go from 0 to infinity because we are facing a random variable x, which is demand, and this demand is always positive. It could be 0 to infinity. So we are not worried from minus infinity to 0 part, because there is no negative demand. We only have positive demand. So we are going from 0 to infinity. So we first put this first part, the random variable x is less than or equal to t. So 0 to t, a t minus x f of x dx, plus the second part, t goes from t to infinity, you have this b x minus t times f of x dx. So we are just using this expectation formula. We copied it right here, split into two parts. Now we expand the first term. You have a t f of x dx minus a times 0 to t x f x dx, and similarly for this second part you have b x f x dx minus bt t to infinity f of x dx. Now we want to differentiate both sides, and that will give us the optimal value. So first let us differentiate this part. So we have to use product rule here because we have a function of t here and this integral is also a function of t here. So first notice that d by dt of integral of 0 to t f of x dx, this is just f of t. Similarly, notice that d by dt of 0 to t x f of x dx is nothing but t times f of t. So basically, if you have t here, you replace x with t. Similarly, if you have t here, you replace x with t. So we are going to use product rule on the first part. So first we have at you keep as such and you differentiate this part. So at we keep as such and we differentiate this part. So you get at times f of t. So because d by dt of this integral is f of t. For the second part, you keep a and this second part as such and differentiate with respect to t. You get a times integral 0 to t f of t dt. But this integral from 0 to t f of t dt is nothing but capital F of t. So that is the definition of the distribution function. The distribution function is from 0 to t f of t dt. We should be writing from minus infinity to t, but that does not matter here because both stock as well as the random variable are positive. So you get a f of t minus, so now we are worried about the second part. Now in the second part there is only one function of t, that is this. So we differentiate this, you get tf of t. So you get minus a tf of t. Similarly here you get b times, you differentiate, we have to differentiate now this part. Now infinity is on the top. What we do is we rewrite this as minus b times infinity to t. So I'm just interchanging this and this, and that's why there is a minus sign, and then you have just x f of x dx. So again you differentiate it, you get t f of t. Just here you consider this infinity as a very large number, and which will be a constant, so you forget about it. So you have t f of t, and that's what you get, minus b t f of t. Then you have this final part here where again you have minus b of t. So we will rewrite this part. So now there are two parts of two functions of t. You have this function of t and you have this function of t. So you use product rule. Again you interchange infinity and t and make this plus sign. You get b t f of t. And for the second part you differentiate this part. We have differentiated this part. Now we differentiate t. So you get minus b times, and you differentiate t, you get t to infinity, and this is f of x dx. Now t to infinity is nothing but, you can rewrite this as minus b times the entire area minus 0 to t f of t dt. Yeah, because this entire area is nothing but 0 to infinity. So again, so the integral from 0 to infinity minus integral from 0 to t will give you integral from t to infinity. And 0 to infinity is the entire area, because we are taking the demand which is positive. So 0 to infinity is the entire area, and that's why you have 1 here. So this is what we write here, minus b 1 minus, and the second part is capital F of t. So now you just do the cancellations and you collect the terms. So this and this will also cancel out. So you get a plus b capital F of t minus b. So notice that if you differentiate it again, you take the second derivative, you will get, the second derivative would be a plus b, and then you would get f of t, which is positive, and therefore we will have a minima here. We will have a minima. So since we have a minima, you can say that we have an optimal cost. So you equate this equal to 0. So equating equal to 0, you get optimal as b over a plus b. So what does this essentially mean? So let me draw this in a graph and show you what does this t optimal mean. So what we do is, so this f is a cumulative distribution function. So you know that this cumulative distribution function, this goes from 0 to 1. This goes like this. So it is asymptotic. When it goes towards minus infinity, it tends to 0. When it goes towards plus infinity, it tends to 1. So this is the function. So this b over a plus b is always less than 1. So this function will take some value here. At this value t, so say this is the axis, so you have 0 here and you have 1 here, and say this is the value t at which you have, at this value t you have a over b over a plus b. So there is some value t at which this function becomes b over a plus b. So this function is monotonically increasing, so you have this unique value here, b over a plus b. So at this value you have the optimal inventory level. So notice the optimal inventory level is where f of this T optimal is equal to B over A plus B.